So now we have the next talk by Viviane Ribeiro Tomaz da Silva, and she will talk about, okay, maybe you can show the first page. Yes, she will talk about classification and polynomial identities of two-dimensional Jordan algebras. She's from University Federal de Minas Gerais, Universidade Federal de Minas Gerais. Okay, please.
Okay. I would like to start by thanking Professor Art for invitation and also all the organizers. I will speak about this topic about the classification and the polynomial identities of two-dimensional Jordan algebras. And this is a joint work with Professor Diogo Diniz from Universidade Federal de Campina Grande, Dimas Gonçalves from Universidade Federal de São Carlos, and Manuela Souza from Universidade Federal da Bahia. I would like to start by giving some motivations, and actually the first part of my talk is about the classification, and then I would like to remember that, for instance, Marcos in 1960 gave a classification of the commutative two-dimensional real algebras, and in 2000, Peterson given a classification, but now of two-dimensional non-associative algebras. But it is interesting that in this case, he works over an arbitrary field, even of characteristic 2. And another classification was given by all of these authors in 2008. And they gave a classification of two-dimensional Jordan algebras, but in this case, they work over the field of the real numbers only. Okay, then now here we would like to give a classification of two-dimensional power associative commutative algebras, but over an arbitrary field of characteristic different from 2. Okay, actually, as a consequence of our results, we obtain a classification for the Jordan algebras because we have proved that every two-dimensional power associative commutative algebra is a Jordan algebra, okay? This is an interesting problem because in general, if you have a Jordan algebra, we have a power associative commutative algebra, but the converse is not true in general. But for two-dimensional algebra, it is okay, and we have proved this, and also as a consequence, we obtain a classification of two-dimensional Jordan algebras over an arbitrary field of characteristics different from 2. Okay, I will give the details later, but it is interesting that in this classification, we also prove that up to isomorphism, we have a unique non-associative Jordan algebra of dimension 2. Okay, all the other ones are associative. And I would like only to remark that this problem about the power associative and Jordan algebras, we also have another papers and, for instance, and results. For instance, we have this result from Rodrigues, Papaneto, and Vanegas. They prove that if you have a power associative commutative algebra of dimension at most 3 over an algebraically closed field of characteristics not equal to 2, 3, or 5, then they are Jordan algebras, which means that in this case, you have if and only if, okay? But not that here you have an algebraically closed field of characteristics, not 2, 3, or 5, okay? It is more specific in some sense, okay? And we also have this another result is that there exists power associative commutative algebras of dimension 4 that are not Jordan algebras, okay? Then in general, it is not true that if you have a power associative commutative algebra, then you have a Jordan algebra, okay? Okay, it is only in order to say some words about this. Now about the second part of the talk. I would like to remember this result of John Bruno, Mischenko, and Zaitsev of 2007. In this paper, they prove that in the general case of two-dimensional non-associative algebras, the codimension sequence is either bounded by n plus 1 or grows exponentially as 2 to n. Okay? Moreover, they construct a family of two-dimensional algebras indexed by the rational numbers with pairwise distinct ideas of polynomial identities and whose the codimension is exactly n plus 1. Then we have this result, and here our second goal is to describe a finite basis for the polynomial identities of two-dimensional Jordan algebra over an infinite field of characteristics different from 2. Okay? Actually, we intended to describe a finite basis as well a basis for the quotient space, and as a consequence, you obtain the codimension sequence in this case. And you prove that the codimension of all of the algebras of two-dimensional Jordan algebras are bounded by n. Okay, then see, in general, it is bounded by n plus 1 or grows exponentially as 2 to n. But for the Jordan algebra, it is bounded by n. Okay, in the end of this talk, I will present the codimension sequences for all the algebras, and we will see that the codimension is in general 0 or 1 for the associative algebras, and for the unique non-associative, you obtain exactly codimension n, okay, is this. And finally, we, as another consequence, we also obtain that there exist two non-isomorphic algebras such that they satisfy the same polynomial identity, okay? And this is interesting because this means that we cannot distinguish Jordan algebra by using polynomial identities. And I'd like to highlight this kind of result because remember, we will characterize the polynomial identities over an affine field, okay? But we are also working in another work, okay? It is not for this talk, but for another one, with about finite fields, okay? And there, actually, we obtain that it's possible to distinguish Jordan algebras by using polynomial identities, okay? It is a curiosity, actually, but okay, it is not for today. Okay, now I'd like to give some definitions, to fix some notations, but actually Plame, Claudemir, Carla give today spoke about this, okay? I will only to repeat in some sense and in order to fix the notation. Okay, then F will denote an arbitrary field of characteristics different from 2. A, F algebra, and Fx, the free non-associative algebra freely generated by X, okay? Then remember that in this case, the elements of Fx are polynomials, non-commutative variables in general, but here, in general, non-associative also. Then we have some parentheses, okay, between the monomials and inside the monomials also, and we needed to take care about them also. And you refer to the elements of Fx are called as polynomials, and we say that a polynomial in Fx is a polynomial identity for A if it vanishes when we replace the elements of the polynomials by the elements of the algebra A. And then we define the associator of 3 elements in this way, okay? We use this notation, and this means this operation, okay? And finally, we have that A is associative if and only if the associator is a polynomial identity for A. Okay, then is an example. In general, if A satisfies a non-trivial polynomial identity, we call A a PI-algebra, and we denote the subset of Fx with all the polynomial identities of A by IDA, and it is interesting that it is at the ideal, which means that it is an ideal which is invariant under all the endomorphisms of Fx. And every time here that I say some words about the basis of this set, I mean basis in this sense, okay, as the ideal. Then, an algebra A is a Jordan algebra if it satisfies the commutator. Okay, Thiago talk a lot about commutators, and we have this definition. And also, not that here you don't have the associator, okay, but the associator with these specific elements, okay, x1 squared, x2, and x1 again, but without square. Okay, then this is a Jordan algebra. And an important example of Jordan algebra is if you have an associative algebra A, then the vector space of A with this multiplication here is a Jordan algebra. And for instance, if you focus on UT and F, okay, upper triangular matrices n by n, then if you take this associative algebra with this product, then this is a Jordan algebra, and you denote this algebra by UGNF. Okay, we use this notation during this talk. And finally, an algebra A is called power associative if the subalgebra generated by n element is associative. Okay, and as I have said before, it is well known that Jordan algebras are power associative, but the problem is with the converse. Okay, then now I'm going to start with our results. Okay, the results together with Diogo Diniz, Dimas Gonçalves, and Manuela Souza. And the first one, it's this lemma that I decided to focus, to say some words about this, because actually this is an essential point in the classification, okay? And actually not only essential, but I think also interesting point in the classification, also in the proof of the classification. Okay, let us take care about this. Take D, a commutative algebra, over a field of characteristics different from 2, such that the square is not 0, okay? Pay attention that we are interested in the classification of two-dimensional Jordan algebras or power associative algebras. Okay, in this case, it is equivalent, but in general not. But the point is that this algebra here, it is in general can have any dimension, okay, any finite dimension, okay. We can think the dimension of D as 3, 4, 5. It is not important for our proof, okay. This is an interesting point, okay. Then take a commutative algebra, finite dimensional, such that the square is not 0. But assume that this algebra satisfies this property, okay? This is the main point. The property is the following. This set, u squared, is a linearly dependent set for every u in D, okay? If you take an element u in D and take u squared, this set is linearly dependent, okay? Imagine an algebra with this property, okay? Of course, since this is linearly dependent set, then u squared is equal to an scalar times u, okay? And then, since this is true for an element of the algebra D, we can define a map from D to F by using exactly this, okay? You take the scalar that appeared here and map u to this scalar, okay? And the first important point is that this map is actually an homomorphism of algebras from D to F, okay? And moreover, this map is not zero, okay, it is easy, this is not zero, and D is a Jordan algebra, okay? Then we prove that actually, when we have an algebra like this algebra must to be a Jordan algebra, okay? Even for any dimension. Okay, then now an interesting or curious point is, okay, give him an example of this algebra, okay, because it seems a little abstract in some sense. Okay, now an example. Okay, take ND and denote by Dn the subalgebra of UGNF, okay, the upper triangular matrices, with T is a Jordan algebra, okay, with that product. But the subalgebra of UGNF generated by these elements, okay, the elements of the first row of the matrices, okay? Okay, take these elements with the product given here. Then this algebra is a commutative algebra such that the n squared is not zero, not that you have the element u1, 1 here. And moreover, if you take an element of this algebra, we can written this element in this way. And when we do u squared, you obtain exactly the coefficient of u1, 1 times u. Okay, we obtain this element. Then see, in other words, we are saying that this algebra satisfies exactly all the properties of the algebra D of the lemma, okay? And in this case, it is clear the map moves U to X1, okay? It is only this, okay? Then we have this example, but okay, the next question is, okay, there are another examples of algebras like this, and the answer is not, okay? Actually, we have proved that if D is a commutative algebra over F of characteristic different from 2, such that D square is not 0 and the dimension of D is n, such that this set is always linearly dependent for every u in D, then D is isomorphic to the n. Okay, then actually we have a unique algebra like this. Okay, and in order to prove this, it is simple in some sense. It's enough to take a good basis for D. Okay, in order to we have a basis here. It's the natural one given by the element, the matrices elements, okay? And the good basis here, it's the basis such that the map moves the first elements of the base to 1 and all the others to 0, okay? And then when we define this map, we obtain an isomorphism of algebras, okay? It is the natural in some sense, okay? Okay, then this is general, okay, for n dimension. And but as I have said, it is a curiosity about this algebra, but also it is important for the proof of the theorem. Okay, here we have the classification. Then take a two-dimensional commutative power associative algebra over an arbitrary field of characteristic different from 2. Then, if J is a power commutative power associative algebra, then J is a Jordan algebra, and if J squared is not 0, then J is isomorphic to one of the following algebras. Okay, I have written here the algebras in order to pay attention that they are not isomorphic. Okay, the first algebra is this algebra here. It is okay. Maybe first, not that the first three algebras are subalgebras of full matrix algebras, okay? And then they are associative algebras. And the last one is our algebra D2, okay? It's the algebra that we are talking about it, but with n is equal to 2, okay? And then this is a subalgebra of UG2F, and it is the unique non-associative algebra. Okay, now, for the first one, it is easy to see that U to 3 is equal to 0, okay? Then this is a nilpotent algebra. Then our first is nilpotent. The second one is this algebra, okay? And we can see that this is this algebra does not have a unity, okay, then actually this is an associative non-nilpotent algebra and does not have a unity, okay? The third one, it's clear that it has a unity, and then the third type, actually, all of them are unique, but this type of algebra, in general, you have more, okay? See here, you have a lambda, and of course, for each lambda, you have an algebra, but I will discuss about the isomorphism in some seconds, actually. Okay, then M lambda is an associative algebra with unity, okay? And the last type, you have seen that it is a non-associative algebra, okay? Then it is clear that everybody here are not isomorphic, okay? The problem is only with this algebra, because actually here we have more than one algebra. And we have that M lambda is isomorphic to M lambda prime if and only if there exists a non-zero element A in F such that lambda is equal to A squared times lambda prime, okay? And then we have a specific condition in order to have or not to have the isomorphism, okay? And okay, then this is the classification, the result. And now I'd like to say some words about the proof of this classification, okay? Only the idea, actually. Then, take a two-dimensional power associative commutative algebra such that G squared is not zero. We have two possibilities, okay? There exists U in G such that U squared is a linearly independent set, or U squared is a linearly dependent set for every U. Okay, you have only two possibilities. I will say first the second case, because actually we have seen everything about this. In this case, we have seen that J is isomorphic to D2. Okay, in this case, we have a two-dimensional algebra. Now, for the first case, that there exists a U in J such that U square is a linearly independent set, we have that we can written U3 as a linear combination of U and U square. Actually, U square is a basis in this case, okay? And then we study the cases based on the scalar alpha and beta. And then, for instance, if alpha equal to beta is equal to 0, here you will obtain 0, and then U23 is equal to 0, and J is nilpotent, is isomorphic to N in this case. In the second case, if A is not 0, if alpha, sorry, is not 0, but beta is equal to 0, then here we obtain U23 is equal to alpha U22. And in this case, if you take this new element V, and then we obtain that V23 is equal to V22, and this one is a basis for J, and it is easy to produce an isomorphism of J with the algebra N that you have seen. And finally, the last case, when beta is not 0, we can produce a unity, okay? It is enough to take the inverse of beta, and then we obtain a unity, and then U1 with U is a basis, but this case is the most complicated in some sense, if we compare these cases, because in these cases you'd like to have an isomorphism with M lambda, okay? And okay, where is lambda? And in order to obtain a good basis in this case, we take W to be this element. And in this case, we obtain that W squared is equal to lambda times 1, where lambda is this element. Okay, and then with this new basis, we can obtain an isomorphism from J to M lambda. Okay, it's only an idea of the proof, but I think that it is interesting to see a little about this. And then, okay, this is the result, okay? And as a corollary of this, we can obtain, for instance, the classification of two-dimensional Jordan algebra over the complex numbers of the real numbers, okay? And for instance, okay, see here that the condition is the following, that, let me go back because okay, now you can see, that lambda is equal to A22 lambda prime, okay? This is the condition. Then, see, if lambda is equal to 0, it is impossible, since A is not 0, if lambda is equal to 0, it is impossible to obtain a not isomorphic algebra, okay? Then you must to have at least lambda equal to 0 and lambda equal to 1, okay? For the complex number, it is enough, okay? We obtain all the other numbers by using this equality here, okay? And then we obtain the classification for the complex, in general, for an algebraically closed field, okay? We have 5 algebras. And for the real numbers, if you take care about this condition here, and then we see that in order to, for instance, in order to obtain the negative numbers, we need to put also the number -1, okay? And if you have -1, 0, and 1, we obtain all the algebras, and then the classification is given in this way, okay? Let me... Okay, then is this, actually this is an alternative proof for that paper that I have, okay, in the beginning of the talk, maybe here, I talk about this work, okay, where they prove about they gave the classification of two-dimensional Jordan algebras over the real numbers, okay? Then here we obtain an alternative proof, okay, for it. And this is the classification here. Okay, this is about the classification. Now I would like to say some words about the polynomial identities, okay? Okay, we have the classification, then it's enough to describe the polynomial identity of each algebra in it. The first algebra is so simple because it is nilpotent, and it's commutative because it's a Jordan algebra. Then, of course, you have the commutator and this identity here, and these identities are enough in order to obtain all the polynomial identities in this case, okay? We also have a basis for the quotient space, and in this case, it is simple, okay? It is this. The second case, we have the algebras M and M lambda, okay? They are associative, remember, commutative, and then, of course, they satisfy the associator and the commutator, okay? And actually, in this case, these two polynomials are enough in order to describe all the polynomial identities. Actually, we also have a basis, okay? It is simple in this case, but I'd like to highlight that not that here, M and M lambda, we have two non-isomorphic algebras, but they satisfy the same polynomial identity. Okay, then in the beginning of this talk, I have said some words about this, and this is the example, okay, of two non-isomorphic algebra which satisfy the same polynomial identities. Remember that all the polynomial identities that we are given now are for the infinite field, okay? The classification is general for finite or not infinite in general, different with characteristics different from 2. But this polynomial identity is in the case of an infinite field, and we obtain this. Now, the last case is the algebra D2, okay, for two-dimensional algebras. But as I have done in the beginning, I will do the same now. I will take care about the algebra D in general, okay, not about D2. Then remember, D is a commutative algebra of any field of characteristic different from 2. D squared is not 0. And the dimension of D is at least 2, but it is not necessary that the dimension is 2, okay? The characterization of the polynomial identities that we will obtain does not depend of the dimension. Okay, this is interesting. Okay, and this algebra is so specific. And then we will present in general the result. Okay, of course, we as a corollary we obtain also for the two. Okay, our last algebra. Okay, in this case, remember that this is the unique non-associative algebra, okay? Then in this case, we need to take care about the parentheses. Then, in order to do this, I will introduce this convention here, okay? Every time that I write this product without parentheses, this means that we have parentheses, okay, in this way, okay? We put the parentheses from right to left, okay? We put the first, the second, and so on, always from right to left, okay? This is the convention that we will adopt here. Okay, the first result is that all of these polynomials are polynomial identities for D. Okay, the first one it is obvious. Okay, this is a commutative algebra. It's okay. The interesting ones are those polynomials, mainly the last one. Okay, see the last polynomial identity allows, in some sense, to put parentheses in the correct order, okay? If you have a product here, or if you have this polynomial here, remember this with this convention here, then this identity allows to do some bridge between this case and this case, okay? And then this is a really important identity. But we also have these two identities, and these two identities, in some sense, tells how to proceed when we have more variables inside the associator, okay? This identity here deal with the case in the first position, actually also in the third position, because we have a Jordan algebra, and then in this case it's similar. But the second identity tells about when we have more variables in the second position. Okay, okay, it is this, and here we will denote by I the ideal generated by these four polynomials, and we use this convention. Okay, we denote this congruence relation between F and G. You say that they are congruent if and only if F plus I is equal to G plus I, okay? Is this. And then the first lemma, okay, it is clear, since all of that polynomials are polynomial identities of D, of course, I is a subset of IDD. And the detail here, but which is important, is that since D is a Jordan algebra, it is clear that this is an identity, okay, for D. But if you pay attention, this polynomial does not appear in our list of polynomials, okay? Then, okay, where is this polynomial? Actually, it is a consequence of our polynomials, okay? This polynomial belongs to I. Okay, here we have the proof, but okay, this is only a detail, okay? We have the polynomial t, which can be written this way, but this is also an identity, okay, because the associator or the commutator, sorry, is an identity, and then this is an identity, it is this. Okay, I'm saying about identity, but also it is an equivalence, okay, with I. Okay, then, but this is important because, see, we have seen that the commutator and now this polynomial, both of them lie in I. And then, if you take the quotient, then the quotient is a Jordan algebra. And if it is a Jordan algebra, then it has these two properties here, okay? The first one allows to change the first with the third position in some sense. And the second one allows to change position between the three positions in appropriate way, okay? And if you deal with this together with this lemma, this is the crucial point, is that if you have n minus 1 variables here in any order, and here the associator with one variable here, then we can order every these n variables, okay? We put in the correct order, okay? This is important in order to try to obtain a basis for the quotient space, and also to obtain a base to prove that this the ideal is actually the ideal of polynomial identities of D. And in order to do this, it is enough to deal with good polynomial. Which is a good polynomial for us? It is a polynomial in this way. Okay, take a polynomial here, some variables with the associator, and then we assume, in order to be a good polynomial, that you have an order, okay? All these variables here and here and here are in the correct order, everybody. And also you have an order between this variable and the last one, okay? Is this. This is a good polynomial for us, okay? Okay, here you have another convention, but for this talk it's not important, okay? I will. And then the result is that if you take H to be the subset of fx formed by all these polynomials together with all the good polynomials, then we obtain that this set form a basis for this vector space. Moreover, if I is an finite field of characteristics different from 2, then the set of polynomial identities of D coincides with I, okay? That 4 polynomials are enough in order to describe all the polynomials of this algebra, okay? Remember that this algebra is n-dimensional, then for the n is equal to 2, we have this result, okay? It's a particular case, actually, okay? Then we have this, and in order to finish, I'd like to say some words about the codimension, okay? In general, we obtain the basis for the quotient space for the free algebra by the set, the ideal of polynomial identities. When we look and focus on the multilinear polynomials, okay, we denote by Pn the set, and by PNA, the quotient space by IDA, and the codimension sequence, then, okay, we have this definition. Today, a lot of speakers talked about this. And finally, I only would like to remember the co-character sequence if sigma is an element of the symmetric group. And then we have an action of sigma in F. F is a polynomial in Pn. And then by permuting variables, okay, it is so simple. And then the quotient, it's an SN modulo, and then its character is called the co-character, okay? And if the characteristic is 0, we have that the co-character is given as a sum of irreducible SN characters. Each one corresponds to a partition, and here you have the multiplicity, okay? It's this. Then, the result is the following. If J is a two-dimensional Jordan algebra over a finite field with characteristics different from 2, such that J squared is not 0, then the codimension of J is given the following way. If n is equal to 1 or 2, the codimension is 1 in any case. But if n is at least 3, and then we have the codimension 0 for the nilpotent case, 1 for associative non-nilpotent, and n for if J is non-associative, okay? And then finally, the co-character sequence, we have 0 if J is associative, nilpotent, and this co-character here, and finally this one in case non-associative. Okay, it's this. Here you have the reference, okay? All of these results are in this paper, okay? Published in linear algebra in its application this year. Okay, thank you very much.
Thanks a lot for your talk. Are there any questions, comments? Okay, I don't see it. Okay, thanks, speaker again.
Thank you.
And